read this introduction here, then we'll look at some illustrations of some collision scenarios, if you like. So I've just made some opening remarks here. So an important task for any virtual environment is to simulate the real physical world environment. And to do that, it has to manage collisions between moving or collisions that happen by objects moving through the environment. Okay, the system has to detect when these happen, or predict when these are going to happen, notice when these are going to happen, and also manage anything resulting from the collision. Okay, which in terms of like modern computer games and that would, might be to, initiate explosions, or initiate the breaking apart of objects, or initiate one object bouncing off another one, or, the objects breaking apart upon impact or something, or, various things like that. So typically to simulate real physical results of these collisions or interactions. Now, in a later chapter, we'll look at some of the aspects of that physical simulation. Okay. Here we go. Such as mechanics and the simulation of real physics in the virtual environment. In this chapter, we're just concerned with detecting when the objects collide. Okay, and looking at the mathematics that lies behind the computer simulation of collision detection. Okay. So this is basically done through the modeling of the objects with basic shapes. Okay, where you're going to use vector descriptions of the basic shapes. So the problem of detecting collisions will be reduced to the problem of detecting intersections between shapes which are described by vectors. Okay. So just to illustrate, some typical scenarios, what we might mean. Yeah. Although it strikes me, this is probably because I'd already lost interest in computer games by the time Tomb Raider came along. I'd become boring by that stage, I guess. That isn't showing too well. But then maybe this is too early for you. Maybe when your first computer games were after Tomb Raider, or did this is your kind of thing? Okay. So what's kind of illustrated here? So Miss Croft is trying to fight this guy, and the gorilla has a rock, a big kind of boulder here. He's about to chuck it at her, or throw the boulder. But a key idea lying behind this is that, the game doesn't simulate the world in a huge amount of detail. It just simulates it or approximates it enough so that you get a realistic experience doing that. And also, it has to take account, to simulate the physics in precise detail requires huge computing power, not available in the computers we have access to, or the game's consoles. So this kind of thing might typically be treated as some kind of sphere, and whether or not it intersects with the ground, to track the motion of the boulder and whether or not it interacts with the ground, that would be to treat the boulder as some kind of sphere and the ground as a plane. So a relatively simple shape which can be described by vectors, and the ground is just considered as a flat plane, and looking at the interaction of those two. Okay, so yeah, the gorilla chucks the rock at her. She jumps out of the way, and she's getting ready to dispatch the gorilla. So she's going to fire a gun, fire a bullet at the thing. Okay, well, the motion of the bullet is just, as far as the game is concerned, is just going to be a straight line. It's not a straight line in the real world, because gravity pulls the bullet down. But, for the purposes of the game, shooting within a room, it travels in a straight line. Again, to describe the figure of the gorilla exactly, and to track whether the bullet is going to hit it, is if you want to do it exactly, it's going to be very complicated, because is the bullet going to come up here and just miss the gorilla, or shoot just through under his armpit, or something like that? Well, you can simplify it a lot and still retain a realistic experience, perhaps by just treating the gorilla as if it was just two spheres, a kind of upper sphere and a lower sphere. And maybe that will be good enough. And then the game or the system will just track whether this line coming out from the gun intersects one of these two spheres. If it does intersect it, it says, okay, the bullet has hit the gorilla. Ouch. If it misses the spheres, then it says, okay, the bullet has missed the gorilla. Now, this idea of treating the complicated object as if it was just a collection of simple objects, these are called bounding volumes. So they're simple volume shapes which bound the object in the virtual environment. And spheres are fairly useful, but of course, spheres start to become not so good. I mean, maybe that gorilla is quite muscly. Maybe two spheres will be a good enough approximation to him. But something like a wolf, well, maybe a cylinder might be a better approximation for the wolf. So again, we're not going to take precise account of the actual bodily form of a wolf in terms of detecting whether the bullet has hit it. The computer just treats the wolf as if it were just some kind of a thick cylinder moving around. And if the line of the bullet goes through the cylinder, then it's been shot, otherwise not, okay? And you can appreciate that the mathematical description of this is, quite achievable, because it's just a cylinder. Cylinder, okay, it's two circular ends and it has a certain length, and the bullet follows along a straight line. All of that can be described using vectors, and the intersection problem solved. You probably starting to think how you'd set up the problem and solve it, looking for the intersection. Okay? Again, that's an example of a bounding volume, where the wolf is just treated as some simple shape which encloses it. Or here I think the tank is going to try and knock down the oil well. Happens a lot. So the tank is going to fire some projectile. Now, the complicated way to treat the oil well would be to think, well, okay, so the oil well has got this main central cylinder, then it's got all these supporting scaffolding, and it's got all these X scaffolds. Okay, the really precise way would be to take full account of the structure and detect whether the projectile hits it or not, and allowing for the fact that the projectile could, whiz straight through the scaffolding and, squeeze through a narrow gap and shoot out without impacting. Now, but for the purposes of the game, you just want to shoot the thing down and get some feedback. For the purposes of the game, and in order to do it efficiently and to have the action happening very quickly and realistically, an approach might be, well, we'll just treat the oil rig as if it was just a simple cylinder. And so we'll shoot something at it, and all we'll do is just detect whether the thing hits the cylinder or not. And perhaps that will give a good enough impression for the player of the game whether or not they hit the thing. Okay. So those are some just scenarios to illustrate typical setups, but also to introduce this idea of bounding volumes. So before we get into all the vector stuff, just a couple of remarks in the notes here, just to make some of what I said a little bit more precise. So yeah, now we won't be concerned here with the details of the implementation of these simulations in terms of, how the computer system marshals the huge collection of objects, how it, generates each frame of the animation, and which bits it animates and which bits are just treated as background. We're not going to concern ourselves with those details. We're just looking at the mathematics of detecting collisions between these bounding volumes. Okay, but just to give us a very simple picture of what might be going on in the simulation, we'll imagine So just reading here, we'll imagine that the virtual environment consists of a number of objects, some of them fixed, some of them moving. And the movement is dealt with by stepping forward in very small increments of time, okay, which probably correspond to the frames of the video animation that's produced, okay? So there's some small amount of time, delta t, which is called the bound of the simulation. So this might be some small fraction of a second, or maybe 1/5 of a second or 1/10 of a second. Obviously, it gets shorter and shorter. It makes the simulation more realistic. And as the computing power becomes cheaper and the computing power of the devices becomes better, then that bound can be shrunk, okay? Because you can simulate more steps in a real-time second, okay? So there'll be some small time step involved. And what the system, just in one sentence, what the system's doing, of course, there's an awful lot of detail to explain here, which is proper, which is more kind of computer programming detail or computing design detail, not necessarily mathematical detail in the sense that interests us. But what it's going to do is that at the beginning of each time, so after it's finished rendering one step of the simulation, so it's at the beginning of generating the next frame, it tests all the moving objects in the environment and detects any collisions that are going to happen within the time delta t. Okay, so at the beginning of each bound, all the moving objects are tested to see if they will collide with any other objects in the environment within that current bound. And if it detects that some objects are going to intersect or collide, then it has to deal with them by either simulating, producing an explosion or whatever, or simulating some kind of real physical interaction between the objects. Okay. Okay, so bounding volumes. Okay, so I've illustrated some of these. We made the point that to precisely track the position and movement of complicated shapes, it's often not necessary to produce a realistic experience. And moreover, to do it in great detail would be very expensive computationally, okay? Would require lots of computer power. Okay? So at some level, a very rough, that gorilla at a very coarse level would be the two spheres. You could make it more precise, but at some level of detail, the objects, the actual shape is not modeled, but they're approximated by the use of standard bounding volumes. And standard bounding volumes are just the standard simple shapes, like like a rectangular box of some dimensions, a sphere, or a capsule. By a capsule, we mean a section of a cylinder with hemispherical caps at both ends. So a cylinder, but not an open one, a cylinder where the two ends are closed off by half spherical ends. Okay, it's like a medicine pill, like one of those large medicine pills. So we saw the gorilla before approximated by two spheres. Perhaps this figure here shows a more detailed level of how you might depict, well, I've said human there, but it could be any ape. We are apes after all. So you'd use a capsule for the torso, 4 capsules for the arms and legs, and a sphere for the head, And so if the computer just tracks the movements and the positions of these, maybe it should use 2 capsules, one for the upper arm, one for the lower arm, to allow the arm to bend. But tracking the figure to that level of precision, would probably be good enough. And if you're just playing the game and shooting at figures and missing them or hitting them, it probably would seem realistic enough. Okay. So that's approximating the figure. Also shown here is what's called an outer bounding sphere. So even though you might be using some detailed description of the object with bounding volumes, you still make use of a very coarse, simplified, just a single sphere surrounding the object. Because one way that can be used is, there's a computational cost to seeing whether a bullet is going to intersect or collide with any of these small bounding volumes around the shape, around the object being modeled, because you've got to test 1, 2, 3, 4, 5, 6 things. So it'd be better to do a quick test first, just if the bullet is going to come anywhere near the figure. So first of all, test whether the bullet is going to intersect this bounding sphere at all. If it doesn't, then you know, okay, the bullet's not going to hit the figure. If the bullet does intersect the bounding sphere, well then, okay, there's a chance the bullet might hit the figure. So then you test for collisions with the precise bounding volumes, as opposed to the outer bounding volume. Okay, so you know that approach might be good. So you can test. You know, you can do a first test, which is very quick. The collision problem with the sphere is one of the more easily solved ones and quicker to calculate. So you do that first, and then if you detect a collision there, then you go and test whether it's actually hit the more precise shapes. Any questions so far? Well, that's just all set up. That's just all the setup to give you context and to understand how the mathematics that we're going to look at eventually relates to kind of the finished product. So what our task is now, and what this chapter is going to do, is solve a family of collision problems between, primarily between linear trajectories. So we're thinking of these shooting a bullet or something. An intersection problem between the linear trajectory of something and one of these bounding volumes. Okay. Right there. So let's look at our first one. So it's, you know, I mean, if you flick through, you just see a bunch of vector analysis and manipulation in the pages. Okay, that's what it's all about. That's the mathematics underlying these things. So the first one we're going to look at is a line and a plane. So what might that typically being used? Well, suppose a projectile is fired towards a building. Okay, and you want to be able to determine if the projectile will hit the building. And the building will be modeled probably as just a collection of planes. So you've got walls, which are planes, and ends of the building, which are planes. Maybe you're going to treat the roof precisely, but that's probably just two planes lent against each other. Okay, so buildings are modeled using rectangular boxes primarily. That's the bounding volume. So the setup of the problem that we're going to solve is shown in the figure on the opposite page here. So here's our plane, and our plane we take as being defined by, there's a single reference point on the plane, a fixed reference point Q. There's a normal vector to the plane. So the fixed reference point and the normal vector, they uniquely define the plane. And the projectile is fired from some point P, some initial point P, and it's got a velocity vector V. This is the origin down here, just the origin is somewhere in the scene. And so the problem is to identify this point R here, to find the point where the line intersects the plane. Okay. I mean, you may even have looked at this in first year vector algebra. Okay. So that's the setup. So the position of the projectile at time t, so you think of time t starts at 0 at the beginning of the simulation of this bound. Okay, so the system is tracking what's happening between time 0 to time, which is like a fifth of a second, so some small fraction of a second. It's simulating what's happening over some time step. So the position of the particle of the bullet, let's say within that time step, is given by the vector equation of the line. Okay, the starting point plus the time t times the velocity vector. That's the object starting in a straight line. The plane has the vector equation. So this is r standing for any generic position vector along the line. This is r here standing for any generic position vector of a point on the plane. This is the vector equation of the plane. Now remember, you'll recall from the previous chapter that the vector equation of a plane is the dot product between the normal vector and the generic point equal to some fixed quantity s, fixed scalar s. And that fixed scalar is exactly the dot product of n with our known fixed reference point q on the plane. Okay. So that point R, which is in figure 3.2, where the line intersects the plane, well, that point R then must satisfy both of these equations, because it has to be on the line and on the plane. And that gives you the point of intersection. The point there at the tip of my finger, it's on the line of my finger, and it's also on the plane of my hand. So that's to simultaneously satisfy both of these. So we impose that by just replacing this R here with the P plus TV. Okay. So we have this equation here. Now, what kind of equation is this? Okay, it's a dot product equation equal to a scalar. What is known to us? What's unknown to us? Well, everything is known to us except the value t. Yeah. We know n, we know p, we know v, and we know s. S, remember, is n dot q, and q is known to us. So everything is known except t. So it's a single equation and one unknown, t, so we ought to be able to solve it. Yeah. And in terms of the algebra, well, you just, what do? You just expand out. Remember, the dot product distributes over vector addition. So this is n dot p plus t times n dot v equals s. Then that's just a linear equation in t. So you just chuck everything over the other side, and you're left with your solution t. Okay? So the time at which the line intersects the plane is s minus the cross product n dot p divided by n dot v. Okay. Of course, what we're dealing here with is whether the line intersects the whole infinite plane. Of course, in the environment, the object will only be some kind of subset of the plane. We'll talk later on about how to detect whether a point is within, that certain subset of the plane. But just looking at the basic problem here of intersecting a line with a plane, this is the solution for t here. Now, is it valid all the time? Well, just be careful. We divided by a quantity here, n dot v, so that would only be valid as long as n dot v is non-zero. So let's just question that. Well, what if nv is 0? Now, when is a dot product 0? Dot product is 0 when the two vectors are perpendicular to one another. Remember? The dot product of two vectors, 0 means the two vectors are perpendicular. So that means the velocity vector of the bullet is perpendicular to the normal vector of the plane. Well, that means the velocity vector is parallel to the plane. So if you've shot parallel to the plane, well, that's the case where the line fails to intersect the plane. Yeah, because it's not going to get any nearer to the plane. Okay, so assuming that the thing was fired from a starting position off the plane, should have specified that start. The initial point of the projectile isn't on the plane already. We'll take that for granted. So if the velocity vector is parallel to the plane, then the line and the plane are never going to meet. Of course, this value for t, so assuming that that's not the case, so assume that that is non-zero, then we're into these three cases here. Well, it may be that you get a negative value of t produced by that quantity, s minus n dot p over n dot v. So what's a negative? A negative period of time. So how is that interpreted? Well, what's actually happening there is, so the projectile will hit the plane if we step backwards in time. Well, that's what happens when you're shooting away from the plane. If I'm shooting in that direction and I want to test if it intersects that wall, so as time goes forward, the bullet moves that way. So if you're getting a negative value of time out, at time equals 0, the bullet was at the tip of the gun. As you go into negative time, the mathematics is extending the line backwards. Backwards in time, it's saying, well, the bullet hit the wall at minus a fifth of a second or whatever. Yeah. So, but in the typical simulation, well, that's not an intersection in terms of the environment because the bullet is moving that way through positive values of time. Okay. So the normal interpretation would be for negative time, the projectile is actually heading away from the plane. It's getting further away from the plane, so there's no intersection. There's no collision. if the t-value, so assuming that's not the case, if the t-value is actually greater than the bound delta t, then there will be a collision, but it's not going to happen within the current bound. So the computer can just update the position of the bullet, can just move the bullet forward, and then go and deal with the other objects in the scene. And it knows that moving the bullet forward, it won't have hit the wall yet. Okay, so it can safely move it forward. Well, just there may be other objects to check for collisions, but in terms of the bullet and the wall, it's safe to move the bullet forward, and we know it won't have hit the wall yet. And then we can render that frame and then go to the next frame and then see if there's a collision. Okay, or it might, store this value of t, and it knows, okay, the bullet's going to hit it in 10 frames time. So when it comes to simulating the 10th frame, I'll need to deal with the collision. Okay. So the kind of the kind of collision case is this case at the end, where the time to collision is less than the bound. So that means the collision is going to happen within this frame. So then the computer has to deal with the collision and go and simulate whatever the physical interaction is going to be. Yeah, whether the wall's going to fall down, or just a little hole is going to appear in the wall, or it's going to explode, or whatever. Okay. So the time of the intersection is given by t, and the position where the intersection is going to occur is just given by p plus tv. Okay, and p and v are known, so we have the position of the collision there, and we can go ahead and deal with it. Okay. Is that okay? Any yes, question? Yeah, so that's like I'm going to shoot this wall. Yeah, we'd have to take account of that. Yeah, maybe that should be there. T equals 0. Yeah, I was kind of assuming with the setup that the point P wasn't on the plane to begin with, because probably if T is equal to 0, we probably would have dealt with the collision in the previous frame. Maybe this should be 0 less than T less than or equal to delta T. Well, that's probably the fine points of the implementation of the thing. But mathematically, we're just looking at the line intersecting the plane. But yeah, the interpretation would be that the object P is on the plane to begin with. Yeah. Okay. So that's that collision case solved. So let's move on to another one. So remember, Tomb Raider lady, Lara Croft, was firing at the gorilla, and the gorilla was treated as being two spheres, quite a rough approximation. So there, the collision problem to solve is the line, the linear trajectory of the bullet, is it going to intersect either of those spheres? So we have to be able to solve this intersection problem here, where there's a sphere somewhere in the scene. It's represented by a circle there in the diagram. And the projectile begins at this point. It's fired in a certain direction. Is it going to intersect the sphere? And this is just one. Okay, this illustrates one case of the intersection where it does intersect it, and it intersects it in 2 points. It enters the sphere at one point and exits it at another. Okay, but obviously, as you vary the vector v, there's other intersection possibilities that can occur as well. Okay. But this illustrates the setup of the vectors and the definitions and so on. So we're thinking of the sphere being fixed first. The next problem is to deal with when the sphere is moving itself as well. So both objects are moving. But if we assume the sphere is fixed, then we've got a fixed position vector c for the center of the sphere. The sphere has a certain radius r, which is part of the setup. The initial point of the projectile p as before, and the velocity vector of the projectile v as before. So that's all the data of the setup. That's all the known quantities. Yeah, it's getting late, so yeah, I won't rush through this. We'll treat this in the next thing. But I mean, maybe I don't need to hand out a booklet. Maybe you know, maybe I should just set you to solve this problem straight away. You know, it's well, you have it there, but it's certainly quite achievable. Sphere is very easy to describe. It's just the set of all points of distance r from the center. We know how to deal with distance in terms of vectors. It's the magnitude formula. So they're the basic ingredients of this collision problem. Okay, so we'll have a look at that later this morning.